In memory of Mr. Dinch and Sir Augie, we have the internal energy of a gas, specifically ideal gases. In our prior videos, we were talking about the kinetic molecular theory, and we eventually found an equation where, with that kinetic molecular theory, we had this idea that kinetic energy could be thought of as 3/2 kT, where K is a Boltzmann constant, T is some temperature, and this 3/2 existed due to the fact that we have objects moving in 3 dimensions, the X, Y, and Z. Because this is kinetic energy, this is the kinetic energy that's contained within an average gas particle, because kinetic energy is like an average temperature, which is that average velocity. But we can also think of this kinetic energy as a stored energy in actuality. Because even though the particles are moving around, those particles as a bulk have some stored internal energy in them. We can use them and that temperature as a heat flow. So what we can think about is if we have an ideal gas, we could say that the stored internal energy, the potential energy U, is equal to 3/2. And then we've got two options here for this. We could say either NKT, or we could say 3/2 nRT. Oftentimes, it's a little easier for us to remember this because we're already using PV equals nRT everywhere else. This version just has a little 3/2 in front. Now, a kind of strange thing does exist with this equation, which we commonly refer to just within our own little class circle here as the Augie-Dinch equation, named after two students who oftentimes would forget this equation. But for this internal energy of an ideal gas equation here, this 3/2 actually represents how many degrees of freedom that the gas has. And essentially, for each degree of freedom, you gain a 1/2 out in front. Right now, we have a 3/2 out in front for a monatomic ideal gas. The reason why the 3/2 are in front is because a monatomic gas can move in the X, Y, and Z directions. So we get 1/2 plus 1/2 plus 1/2. 3/2. But we can create other types of gases here, or other type of molecules, should I say. If we have something that's diatomic in nature, then it's not just set up as a kind of a ball moving around. This would be monatomic, moving in X, Y, and Z. But if we had something that was diatomic in nature, where it had some sort of shape to it, let's just make like a barbell. Then an object like this, not only could it be moving in the X, Y, and Z directions, like this pencil or pen, but it could also rotate, okay? And in rotating like this, we actually gain more degrees of freedom. For a diatomic molecule, we actually gain 2 more degrees of freedom, and this 3/2 out in front would become 5/2. You can create higher order objects or molecules. You actually get up to 7/2 if you start thinking about the different shapes that you can create here, as well as the fact that I've kind of drawn this as a barbell with a straight bar here. But when we actually think about intramolecular forces, this could actually be more considered as like a spring. Really, it's some intermolecular force that could be existing there. So we can kind of get a oscillation like this, which gives us 2 more forces for 7/2. And if you get really high energy stuff, you can actually get into the quantum domains, which give you 9/2 for 9 full degrees of freedom there. So you can get some like really, really weird stuff. I've never dealt with anything greater than 9/2 degree of freedom. Who knows if something like that exists? If you're in your PhD and you're like, hey, I'm working with something that's 11/2 for 11 degrees of freedom, like, please comment below and let me know. I'd love to hear about it. But this is just generally what's happening with this internal energy for an ideal gas. Each of the molecules here is moving around. It has degrees of freedom, and these degrees of freedom put together give us the 3/2 nRT, or what we might see sometime is a diatomic element for 3/2 nRT as well. The only times you'll see diatomic in this class is they'll be explicitly stated. It'll say something like this is diatomic blank. If you remember anything about your chemistry, though, diatomic things are often things like oxygen, where it's written O2, or I believe N2, H2. There's a whole like slew of them, right? But that's a chemistry thing, and blah, so blah. But generally speaking, within our class, we will explicitly state if something is diatomic or not. So most of the time we're using 3/2, but sometimes you have to use the 5/2. Okay? In our next video, we're going to take a look at why knowing the internal energy of something is important, because we are going to start getting into our 3 laws of thermodynamics. But until next time, adios and take it easy.